Hi everyone, welcome to another episode of CUDA Mode. Today, I'm super glad we have Izzat Haj who's joining us again from as a professor from the American University of Beirut to talk to us about the scan algorithm. So this is part two of his live programming sessions. As that's actually also one of the co-authors of the PMPP book, which we've been using for all of our lectures. So I'm super thrilled to have him again, and thank you, Izzat.
Thank you, Mark. It's a pleasure to be here again. So I'm gonna quickly recap what we covered last time about scan, and then I'll start with the new content. So last time we introduced scan, we said that a scan operation is where if you have some input, the output at each index is going to be some operator applied to all the elements at the corresponding index in the input and preceding that. So for addition, if our operator is addition, the output at index 3 is going to be the sum of all the elements in the input from 3 and before. So 3 plus 6 plus 7 is 16. And this is kind of a generalization for any arbitrary operator. We said that the way that we do scan on GPUs is we segment it. So we'll divide our input into segments. We'll have a thread, and the reason is that we need a lot of synchronization among threads when we're doing the scan operation. So we'll divide it into segments. We'll have every thread block take a segment, scan that segment, and then we'll scan the partial sums of the thread block, and then we'll go back and have every thread block go and add the scanned partial sum to its own elements so that we have a kind of we started by looking at one algorithm for doing scan in parallel. We observed if we just do a reduction tree, we get some of the results that we want for scan. If we do another reduction tree, we get some other results. And if we keep doing reduction trees, we eventually get all the results that we want. And if we overlay all these reduction trees, we get something like this. It's basically where we iterate, and at the first iteration, we have to every element we add the element that is 1 before it. Next iteration, to every element we add the element that's 2 before it, etc. Of course, assuming that the element before it is within bounds. To parallelize this, we assigned a thread to every position in our array, and that thread was responsible for adding an element to the element that is tried before it on each iteration. Of course, what we did is we put this array in shared memory. So these are successive snapshots of the same array, and we put that in shared memory so that when we load and store to it on successive iterations, we don't have to go to global memory. And we also observed that in our initial implementation, we distinguished between two different sync threads. One of them that was enforcing a true dependence, and another one that was enforcing a false dependence. True dependence is where we need to wait for a thread to finish writing something before we read it. And here, it's a true dependence because we really need to wait, right? I cannot read something before it gets written. Whereas the false dependence was where we don't really need it's where we wait for a thread to finish reading something before we write to it. And that dependence is only there because we're using the same memory location to write to where the previous value was. But we don't really need to wait for that value to be read in order to write for the sake of the computation. So we can eliminate this async threads that enforces a false dependence by doing something called double buffering. So where we use two different buffers for the input and the output, and we can alternate these buffers on each iteration. And by using two different buffers, we no longer have the situation where I need to wait for somebody to finish reading before I write, because I'm not writing to anywhere that somebody else is reading. And that helps us get rid of that second buffer. And that's not just an optimization we encounter in scan. Double buffering is used wherever we have a false dependence that we'd like to eliminate a synchronization for. We ended by talking about work efficiency. We said that work efficiency is we say that an algorithm is work efficient when the parallel algorithm does the same amount of operations as the sequential algorithm. But we observed that in the Kogge-Stone parallel scan, it does O of n log n operations, whereas we know that in the sequential scan, we only do O of n operations. And that shows us that this algorithm for doing scan is not work efficient. Now, sometimes work efficiency is a price that's okay to pay because it gives us parallelism. But if resources are limited and we end up starting to serialize the computation, because we're doing one thread block at a time, because we don't have enough assemblies to accommodate all the thread blocks. That's where that work efficiency will start. We'll be paying that work efficiency unnecessarily. And we're going to talk today about how we can address, improve the work efficiency of scan. So last time I also introduced, but we didn't implement it, but I introduced another approach for doing scan, which was more work efficient, but took more steps. We call this Brent-Kung. Someone commented that it's also called Belloc scan in the literature. So here you do a reduction tree, but then instead of doing many reduction trees at the same time, you just kind of do some steps after that that help you finish off that help you finish off the elements that are still not complete. So this approach on the right, we call it the Brent-Kung approach. It takes more steps, but it does fewer operations. So you can tell that the number of arrows that we have over here, or the number of additions, is much fewer than the number of additions that we have here on the left. And we analyzed that, and we found out that the Brent-Kung approach takes more steps. You need 2 log n minus 1 steps compared to log n for the Kogge-Stone approach. However, it does O of n operations, which means that it's more work efficient than the Kogge-Stone approach, which is O of n log n. So we ended up by asking the question, which one is faster? Is it the one that takes fewer steps, or the one that is more work efficient? And what we're going to do today is we're going to implement this Brent-Kung approach and test it and see which one is more work efficient. Okay, so let's get started.
Yeah, so I do want to mention, everyone, if you have any questions to ask us, that like feel free to raise your hand, and we want to make this session interactive. Thank you.
Thanks. Okay, so I'm trying to get the zoom ribbon out of my way somehow. Okay. So we observed that in scan we have this reduction stage and we have this post-reduction stage. So we're going to have a similar approach where we iterate through the stages, and every time we're going to have a thread be responsible for some element and adding a value, an element that is tried away to that element. So we're going to assign a thread. This time we're going to, unlike Kogge-Stone, we're going to assign a thread to every other element, right? Because on the first iteration, for example, we're adding 2 elements and producing 1 result. So we're only producing half the number of results that we have input elements. So we don't need a thread for every single element. So we're going to have 1 thread for every other element. We'll do the same thing we did with the Kogge-Stone approach. We're going to put this array in shared memory. So we're going to load the input to shared memory, do all these scan steps inside of shared memory, and then write the final result to global memory. One thing to note here is that we don't need double buffering. And we don't need double buffering because we don't have a situation here where a value is being read, and then some thread is reading a value and some other thread is writing it. In the Kogge-Stone approach, we had another thread here that was reading this value and then adding the previous value to it and updating it. But we don't have that for this algorithm, and that's why we don't need double buffering. We don't have any race conditions. Okay, so another optimization is the following. So in the Kogge-Stone approach, we assigned a thread to each input element, or to each position in the array, and that thread kept processing that position for every iteration. But if we do the same thing for this approach, we end up to have some kind of inefficiency, and let me show you why. So let's assume that we assign a thread to each of every other position. So I assign a thread to indices 1, 3, 5, and 7. On the first iteration, all these threads will be active. On the second iteration, what's going to happen is that 2 of the threads drop out. Now, in the previous approach, the threads were also dropping out, but they were all dropping out from the beginning of the thread block. Whereas over here, the threads don't all drop out from the beginning of the thread block. They drop out from kind of the middle of the thread block. So they drop out in these arbitrary positions. Well, not arbitrary. Every other thread is going to drop out. And then if we keep going, more threads drop out. And then later, as we do the post-reduction phase, the threads start coming back, and then they come back. But what you see is that in these intermediate stages, the way that the threads drop out result in us having a thread that is active and then a thread that's not, the thread that's active, the thread that's not, the thread that's active, the thread that's not. The next iteration, you're going to have, 3 threads that are not active and then 1 that's active, 3 threads that are not active, 1 that's active. And what this does is it results in control divergence. In other words, in a single warp, we're going to have some threads that are active, some threads that are not, some threads doing useful work, some threads that aren't. So that's going to waste some of the resources of the GPU. And we can get around this control divergence by instead of assigning a thread to a fixed position in the array throughout the computation, we can reassign the threads to a different position every iteration. So instead of doing what we have on the left, we can do this. So we can reassign the threads on each iteration. So on the first iteration, we're going to have all our threads are going to be active, right? But on the next iteration, instead of having the threads drop out from the middle, what we will do is we will move the threads around. So now the first thread is going to be responsible for this addition. The second thread is going to be responsible for this addition. And then the other threads are going to drop out from the end. So now we don't have control divergence because we're going to have some warps that are active and some warps that are not. We're going to have idle warps, but we're not going to have threads inside the same warp where some are active, some are not. Eventually, we will last few iterations where we just have one warp that's active, but that's kind of unavoidable. And then we keep doing that. So in the next iteration, the first thread now is going to do this position, whereas the other threads are going to drop out from the end. So we have this thread here is moving from this position to this position to this position. And then we do the same thing as we go back. So as we go back, we bring in the first thread to do this addition. And then in the next iteration, we're bringing the first 3 threads to do these additions while keeping all the inactive warps at the end of the thread block. So this reassignment of threads on every iteration is a common optimization that we do in different scenarios whenever we want to get rid of control divergence. We change how we are assigning threads to the data so that we always have all our active threads together and all our inactive threads together. So with that, let's go and so reassigning these threads requires some kind of tricky index computations to be able to kind of figure out how to reassign these threads every time. So here, there's actually a kind of a simple index computation that we can use to determine what a thread is responsible for in each iteration. So basically, the index of the element the thread is responsible for is going to be the thread index plus 1 times 2 times stride minus 1. I'm not going to get into too much detail on how kind of we arrive at this. But, if you think about it for a while, it's not too difficult. Basically, you think of, okay, what is the first element what is the first element that the first thread is responsible for? We go from 1 to 3 to 7, so that's basically 2 times stride minus 1. And then on the first iteration, when the stride is 1, we're skipping 2 elements to get to the next thread. When the stride is 2, we're skipping 4 elements to get to the next thread. So basically, we're also going to add 2 times stride times the thread index. So this is how we arrive at this indexing right here. Okay, so let's go and implement this and compare it to our previous implementation that we had in our last lecture. So I'm going to switch to the code terminal. I'm going to start by compiling. Okay, I'm going to start by compiling and running. So this is our previous implementation of using Kogge-Stone. So this is how much time that implementation took. And now let's go and implement the one that I just described. So I already set up some host code for calling that kernel so that we only have to worry about implementing the scan kernel itself. Okay, so this time around, we start by identifying the segment and global memory that the thread block is responsible for. Okay, now before that segment was basically at block index times block dim, because if a thread had 1024 if a block had 1024 threads, it was responsible for 1024 elements. This time, if a thread block has 1024 threads, it's going to be responsible for twice that number of elements, because in the first iteration, every thread takes 2 elements. So we're going to identify the first. We're going to identify for every thread block where this segment that is responsible for is in global memory. Since every thread block is responsible for 2 times the number of threads elements, we find the beginning of that segment by doing block index.x times blockdim.x times 2. Okay, so block 0 is going to start at the global index 0. Block 1 is going to start at the global index blockdim times 2, and etc. Now again, disclaimer here, I'm using kind of macros. The better practice is to use templates. I just use macros because when you're live coding, it's easier to just add a macro and use it as opposed to having to go and templatize and go and modify where everything's written. But the good practice, of course, is to use templates for these constants, also to use templates for the types so that your kernel is general for different types. But to kind of just keep the code simpler, and I don't do that kind of in these live examples. Okay, so now we've identified where a thread block, where the segment of a thread block starts. The next step is for the thread block to load the elements that it's responsible for. Now, what we are not going to do is we're not going to have this thread. If this thread is responsible for these two elements, we're not going to have this thread go and load this element from global memory and then load this element from global memory. And the reason is if we do that, we're going to have poor memory coalescing, because when each thread loads the first element, it's going to load it. We're going to have one value loaded and one not, one value loaded and one not. So we're going to not be fully utilizing that burst. We're not going to be utilizing the cache line. We're going to have poor memory coalesce. So instead, what we will do is we will have all the threads. So if we have 4 threads here, we're going to have these 4 threads load the first 4 elements into shared memory. And then we're going to have the threads load the next 4 elements into shared memory. And then we sync threads, and then each thread will go and access its 2 adjacent elements from the shared memory. That results in better coalescing when we're loading from global memory. Okay, so we'll start by loading the data to shared memory. I'm going to declare a shared memory buffer, where we can put this data. I'm going to call it buffer underscore s. And the size of that buffer is going to be the number of elements that we want to load. So in this case, we have twice the number of threads in the block. So 2 times the block dimension. Okay, we're then going to every thread is going to load the threads are going to load the first number of block dim elements, and then they're going to load the next block dim elements. So the way we do that is by doing buffer underscore s of thread index.x. So thread 0 is going to write to buffer of 0, thread 1 is going to write to buffer of 1, thread 2 is going to write to buffer of 2, is equal to input of segment. So we go to where the segment of the block starts, plus thread index.x. Okay. And then, of course, so now when we do this, every thread, the first 1024 threads have loaded the first 1024 elements. Now we're going to load the next 1024 elements. So we're going to do the same thing, but we're going to add block dim to our thread index. So here we're going to do plus block dim, and yikes. Excuse me, my terminal is lagging a little bit, so this is why there are some glitches happening. Okay, and then here we'll do plus block dim. Okay. Now, of course, after we're done loading to shared memory, we're going to sync threads, and now we are ready for. And now we're ready to do our scan tree. So we'll start with the reduction stage. In the reduction stage, in our first iteration, our stride is 1, next iteration stride is 2, and we keep going until we get to the stride, which is block dimension. Okay, so we're going to use the stride as the loop index. We're going to have the reduction phase. We're going to write for unsigned int stride is equal to 1. Stride is less than or equal to the block dimension. Stride equals stride times 2. And then on each iteration, what's going to happen is every thread is going to identify which element is responsible for. We said that this expression right here helps us identify that. So write unsigned int I. This is the index of the element the thread is responsible for in the shared memory buffer. It's the thread index plus 1 times 2 times stride minus 1. So thread index.x plus 1 times 2 times stride minus 1. Okay, so now every thread knows what element it's responsible for. What it's going to do is it's going to add to the element that is responsible for the element that is stride to the left, right? So we're going to do buffer underscore s of thread index dot x, sorry, of I, plus equals buffer underscore s of I minus stride. Okay. Now, of course, not all the threads are going to be involved in this, right? Some of the threads are dropping out. So the way that we know whether a thread is going to be active in a particular iteration is if the element that it's responsible for is within the bounds of the shared memory buffer that it's working on, right? So the way we do that is by checking if I is less than or equal to 2 times the block dimension, because the shared memory buffer is 2 times the block dimension in size. So we just make sure that that index is within bounds. Okay. So by this, we would have, of course, we also need to sync threads over here to make sure all the threads finish adding on the current iteration before we proceed to the next iteration. And now we're done with the first reduction phase, which is this phase. Okay. Now we're in this situation, and what we need to do is we need to do this post-reduction step. So in the post-reduction step, I'm actually assigning the thread to the left element in the addition as opposed to the right element in the addition. It just makes the indexing easier that way and makes the indexing the same as the indexing in the previous iteration. So let's do the post-reduction phase. So this is the post-reduction. We're going to start from stride block dim over 2 this time, right? And we're going to keep going down until we get to stride 1. Okay. So for unsigned int stride is equal to block dim over 2. Stride is greater than or equal to 1. And then we divide the stride by 2 on each iteration. Okay. And again, this time the element is responsible for, we use the same indexing that we used before. This also works for the post-reduction step. It's the same. So I'm just going to copy that over. Okay. But this time what we're going to do is, since the thread is going to be assigned to the left element, the thread is going to add its element to the element that is stride to its right, so I plus stride, and then it's going to put the result at the position I plus stride. Okay, so we're going to do buffer underscore s of I plus stride, and we're going to add to that buffer underscore s of I. Okay. And again, we need to make sure that the elements that we're accessing is in bounds. We need to deactivate the threads that are kind of at the end and not supposed to be doing anything on that particular iteration. The way we do that is we check and make sure that the element at I plus stride, right, is within bounds. So in this case here, this thread doesn't have anything at stride after it, so it's not going to be active. So we're going to have to come here and make sure that if I plus stride is within the bounds of the shared memory buffer, which is 2 times the block dimension.
Hey, Azad, I just had a quick question. Like, maybe
Go ahead.
not quick question, but like, I'm sort of curious. Like, I mean, like, as you're like authoring kernels and like putting sync threads in it, I'm wondering, like, do you sort of usually write the sync threads like defensively, as in you sort of put them in to be safe and then sort of slowly remove false dependencies, or do you just like write the unsafe code first and then like later put them once you notice that you get incorrect results?
No, I'd rather write code slowly and get it right, or as much of it right as the first time than to kind of go back and have to debug it. So no, I don't recommend putting sync threads in defensively, right?
Mhm.
You should put a sync threads where you know that you need to have a sync threads there. And you should with experience you should always be able to reason about whether you need to have a sync threads or not, right? It's not some so you shouldn't just kind of put it there just to be safe. You
Mhm.
either need it or you don't. So it's good to reason. It's good to stop, think, reason about that. Um, better than having any race conditions. Also, CUDA has some tools like the race checker that also will tell you if you have a race condition and you're missing a sync thread. So that's also a good way to check if you're missing any sync thread. But yeah, it's not good to put in a lot of sync threads defensively because those will hurt your performance ultimately. The sync threads is not just about the latency of the sync threads itself. The sync threads will prevent the compiler from being able to reorder instructions across the boundary of the sync threads, and reordering instructions is important for latency hiding. So there is really a high cost to having async threads where you don't need it.
And so tools like the race checker, are they kind of like a sampling based tools? Like they sort of try to basically like look for like memory corruption, or like how do these tools like generally work?
Um, um, so I've actually I haven't thought much about how exactly the race checker is implemented. I don't know how much of it is based on compiler analysis and how much of it is based on doing the actual runtime analysis. But yeah, the race checker will basically try and check if you have any situations where different threads might be accessing the same memory location and one of them is writing. And if it is, it'll warn you and tell you, hey, you might have a race condition here.
Yeah, makes sense. I would imagine it's probably some combo of both. But yeah, thank you. That really helps.
Yeah, welcome. Again, that's probably something to ask to somebody at NVIDIA who kind of develops that SDK. I'm not 100% sure how exactly the race checker is implemented. Okay, so now that we're done with the post-reduction, the final thing that we need to do, we have our final result. Now we have to go take that result and write it back to global memory, right? So we're gonna do the same thing that we did before, right? We have twice as many threads. Have our threads together write the first half of the array, the shared memory array to global memory, and then write the second half of the array to global memory. Okay, so we're gonna write the output. So we're gonna do output of the output is also gonna start at the segment of the blocks. So we're gonna do output of segment plus thread index.x is equal to buffer underscore s of thread index.x. Right, so here every thread 0 is going to write the value at segment plus 0, thread 1 at the value of segment plus 1, etc. And then we're also going to have then the threads move to the next block dim threads and write all of those out in a coalesced way as well. So here we're going to do plus the block dimension, and here we'll also do plus the block dimension. Okay, so now we've written this scan approach and implemented it in our kernel. So let's compile it, run it, and see how it performs compared to the previous implementation. I'm going to compile. Let's hope we don't have any bugs in our first try. Okay, we do have a bug. I hate it when that happens.
I imagine this is the first time it's happened, probably.
No, certainly not. Yeah, let me quickly try and figure out why this is the case. Otherwise, I'll. Okay. So what I forgot to do is remember that we were when we were doing a segmented scan, right? So we're doing a scan of every thread block does its own scan, and then the thread block needs to write its partial sum out so that we scan those and we go back and we add them. So I forgot to do that. So basically, one of the threads in the thread block is going to be responsible for taking the sum for the entire thread block and writing out to the partial sums, and I forgot to do that. So if we'll do if thread index.x, we'll have the last thread do that. So basically, the last thread will take this last value right here and will write it out as the partial sum of the entire block. So if thread index.x is equal to block dim minus 1, then in this case, it can be any thread. It doesn't have to be this one. It can be thread 0. then we will do the partial sum of the block index.x is equal to the last element in the buffer. So in this case, it's 2 times the block dimension minus 1. Okay, so we just forgot to write out the partial sum. That's what caused the bug. So let me compile it again and let me run it. Okay, and we still have a bug. Oh. Hmm. Okay, I'm not gonna spend time debugging live. I will kind of take a look at it afterwards and let you know where the bug was.
I actually, there are some people in chat that are guessing. We have both Ivan Litov and Yash saying maybe the stride should be less than or equal to the block dim.
No, I have the correct code right here. This code right here is already tested. The stride is less than the I plus. Oh, you're right. Yes.
Okay,
Oops. Okay. There
chat
we
was
go.
paying attention. Good job, guys.
I had a typo right here. There we go. That's the bug. You're right. I don't know why I put greater than or equal to. That doesn't make sense. Okay, so we're gonna compile this. Thank you for catching the bug. Thank in the audience, and we're gonna run it. Okay, there we go. And now that works. And now if we compare the time, you'll notice that it's actually, this was the time of our original Kogge-Stone implementation, and this is the time for our Brent-Kung implementation. So you'll notice that the time is slower. So even though this implementation is more work efficient, ultimately it results in slower performance. So this having more of these iterations and more of these synchronizations ends up hurting performance ends up hurting performance more than the benefit that we're getting from improving the work efficiency. So while the Brent-Kung has higher theoretical work efficiency, right, in practice, the work that we reduced, right, we're doing less work. The warps that we're doing that work now are actually just not doing anything. They're idle, and because this is kind of a latency bound operation when it's doing those different stages. The work that we're saving was previously just filling in pipeline cycles that are now just being filled with stalls. So we don't really see that major improvement from improving the work efficiency. So the performance of Brent-Kung on GPUs is similar and maybe even worse than the Kogge-Stone approach. It's still an interesting case to study because it allowed us to reason about work efficiency. Okay. However, as you can see, the more work efficient algorithm is not always the best algorithm to follow. Okay. Okay, so that's all in terms of comparing Kogge-Stone approach and then Brent-Kung approach. I want to talk more about how we can improve work efficiency other than using a different algorithm. So if you want to stick to Kogge-Stone because it gives us fewer steps, is there another way that we can improve the work efficiency of the Kogge-Stone approach? And the answer is yes, and that's through something called thread coarsening. So what do I mean by thread coarsening? Thread coarsening is kind of a general category computations. We don't pay anything to parallelize the computation. So, for example, in vector addition, when you do it in parallel, there's no parallelization overhead. But in other computations, when you want to parallelize the computation to go from a sequential implementation to a parallel implementation, there's an overhead for doing that parallelization. There's a price that you pay to extract that parallelism, right? In our case over here in scan, the price that we pay to extract that parallelism from scan is that we use a work inefficient algorithm. We are doing more computations to be able to extract parallelism. We're also doing all the synchronization overhead. So now, if you actually get all these threads running in parallel on the GPU, right? That's great. The price that you pay to extract that parallelization is worth it, right? Because you're actually getting parallelism. But as we know, when you write a kernel, if you have more thread blocks than the number of thread blocks that can be simultaneously occupied on the GPU, what the hardware does is that it'll run some of the thread blocks. When they're done, it's going to bring in other thread blocks. When those are done, it'll bring in other thread blocks. So if you give the hardware more thread blocks than it can actually handle, it's just going to serialize those thread blocks. Now, if we have something like vector addition where that parallelization came with no overhead, it's okay to do that because the hardware scheduler is fairly quick at taking out a thread block and bringing in another one. But if you paid some kind of price to extract that parallelism, and then the hardware scheduler ends up serializing those thread blocks, you paid that price for no reason. So it's better for, instead of letting the hardware serialize that work, you can serialize that work in your implementation and get rid of the overhead that you paid for parallelizing it. So in the case of scan, that overhead was the parallel scan, which is work inefficient. So what we can do is we can instead have every thread do a sequential scan. So instead of have every thread take a single element, we can have every thread take a chunk of elements, do a sequential scan, and we know that sequential scans work efficient. It does O of n operations. And then after doing that sequential scan, we go and we do a reduction tree across the entire thread block. So to recap of what I said, parallelizing scan incurs the overhead of lowering work efficiency. We also have the overhead of doing these barrier synchronizations every step of the Kogge-Stone iterations. So if the resources are insufficient, the hardware is going to serialize those thread blocks. So we'd have paid that overhead unnecessarily. So it's better if we apply thread coarsening by doing a segmented scan at the level of the block, right? Where we segment our scan across threads. Every thread does its own sequential scan, which is work efficient. And then we use the thread block to scan the partial sums of the threads. And that looks like this. So before, we had every thread block. We were segmenting the scan across thread blocks. Every thread block was doing its scan, we were scanning the partial sums, and then we're going back and adding in each thread block. Well, we can use that same approach to have every thread responsible for more than one element and do a sequential scan. So here we can take that individual block scan, segment it across threads. So every thread now is going to take a segment in our input instead of a single element. The thread is going to do a sequential scan of that segment, which is work efficient. It does O of n operations, where n is the number of elements in the segment. And then the thread contributes those partial sums. We use the thread block to scan those partial sums in parallel. And then every thread is going to go back and add that value to its own segment. Okay. So Mark, you had your hand up.
Yeah, like I had a question around like coarsening in general. Like it just seems like it's like one of the more interesting optimizations because like at the limit where you have like one thread handle all the elements, like that's terrible. But then it's very common that having like one thread handle one location in memory is also terrible. And so I'm sort of like wondering, like, is there like a curve where like it's sort of more efficient, like there's like a certain coarsening factor is good? I think we tried this in the past in these lectures during the reduction kernels. Uh, and it was like very much a benchmark and see kind of approach, but I'm wondering if you have a sort of more principled way of thinking about like what is a suitable coarsening factor.
So yeah, when you pick a coarsening factor, obviously you can't go all the way. You don't want to go all the way because otherwise you're just gonna have one thread doing everything. You're gonna significantly underutilize the hardware. So you want to pick a coarsening factor where you're still fully utilizing the hardware, but not exactly. But you don't want exactly the number of thread blocks that can run simultaneously on the GPU. You probably want to have a little more than that to let the hardware scheduler still be able to do some load balance. It depends on the computation itself, how much load imbalance it has. But you probably want to have a coarsening factor that'll give you maybe 4, 8, or 16 times the number of thread blocks that you have that can actually run simultaneously. That's assuming you have a fairly load balanced computation. If you have a more load imbalance computation, in that case, you're going to need to give the hardware scheduler more just so that it's better able to do load balancing. So it's usually I would that's something you can tune. You can try different values, see what works. But for the range of values, you probably want to look at picking a coarsening factor that helps you kind of have as many thread boxes can run simultaneously, but also have multiple times that to help with load balance.
But
there are cases actually where sometimes go ahead.
No, like because you mentioned something, I don't know if it was implicit, but like basically it's better to make sure that your work is more load balanced. So basically make sure that you don't have like divergence and then basically and then coarsen. So like the order matters in which you're dealing with those optimizations. Okay, that's very interesting.
Yeah, so divergence has to do with balance across threads in the same war. When I talk about load balance in this context, I mean more balance across the different blocks.
Oh, got it.
But yeah, another thing to consider is sometimes coarsening is so beneficial, especially when it allows for higher data reuse, that we actually don't mind running at lower occupancy. And that actually happens in some of these very sophisticated matrix multiplication kernels. In some of those cases, we actually don't run at full occupancy, but because by doing more thread coarsening, we're able to capture more data reuse, and we're willing to pay the price of having lower occupancy because we're able to have more data reuse.
There is one more problem with coarsening, and I think we should acknowledge that when you coarsen too much, you are also adding a lot more pressure to your registers. So if your application is register bound, coarsening may or may not actually help you. So you'll have to bound the number of register per thread, and you can end up getting register spills that can severely impact your overall throughput.
Right. Yeah, you're absolutely right. So yes, so thread coarsening, as Vikram said, it uses more resources, so it affects your occupancy. But like I said, in some cases, you actually don't mind. So in some matrix multiplication kernels, you actually don't mind running at lower occupancy because you're getting the benefit of data reuse of using more registers per thread, for example, which gives you better data reuse. So those are the situations where you need to tune your coarsening factor to see kind of what works best for you. Okay, so yeah, so this is how we would apply thread coarsening in the context of scan, and this gives us a more work efficient implementation because the sequential scan is work efficient, right? We only do O of n operations, and then we're only incurring the work inefficiency when we are combining these values when we're doing the reduction across the different thread blocks. Across different threads in the block. Okay, so let's go implement this and see what it looks like in the context of scan. So I'm going to switch to my terminal. This time I'm going to go today. Okay, so I already prepared. This is the kernel that we had before from Kogge-Stone, but I already prepared the host code for doing coarsening just so that we don't have to go through that. So basically, this time what we're doing is we're launching. Oh yikes! Oops. I'm sorry. The code is already filled in. This was unintended. I apologize. Okay. So, why did that happen?
I think you just wrote it so fast that like we just couldn't even.
Yeah, I think it seems I copied the wrong. I usually have a skeleton before and then the after, and it looks like I copied the wrong directory here. Okay, so I guess I'll walk you through the code instead of implementing it. I apologize for this mistake. So basically, what we do is we're going to allocate a buffer And then we are going to have, we're going to first have the threads load from global memory into that buffer, right? So the if we have a coarsening factor of 8, for example, in this case, we're going to have the threads iterate. Every thread, instead of loading a single element, now it's going to load 8 elements. So we're going to iterate 8 times, and each time the threads are going to load a consecutive chunk of elements from the global memory to the shared memory. Of course, we're going to load it in a coalesced manner. So we're going to have, if we have 1,024 threads, we're going to have them load the first 1,024 elements, then the next 1,024 elements, then the next 1,024 elements. We're not going to have thread 0 load the first 8, thread 1 load the next 8, because that's not going to result in good coalescing. Okay. Once we have done that, once we've loaded these elements, okay, the next step is for every thread to do its own sequential scan. So over here, the thread is going to iterate. So here, every thread is responsible for 8 elements to do a scan across these 8 elements. So every thread is going to iterate over these 8 elements and do a scan of these 8 elements. That's happening right here, right? After that, every thread is going to contribute the partial sum of its 8 elements to the block scan, right? So if we go over here, every thread did a scan over its 8 elements, then every thread is going to take the element that is at the end of its segment. So here we access the shared memory buffer at the beginning of a thread segment plus coarsening factor -1, so +7. That's the last element in the thread segment. And we put that in the in buffer, which was the buffer we were using previously to do the Kogge-Stone scan. And then the rest of this code is doing our scan operation from before. So this hasn't changed, right? And then after that, the last thread block is going to write out the partial sum. So this also hasn't changed. But then at the very end, now we have this array right here. What we want is for, sorry, now we have these scanned partial sums right here. What we want is for every thread, what we want is for every thread to go and add its value to to add the previous thread's the partial sum of all the previous threads to its own elements. So that's what's happening here, all except the last thread, right? Because sorry, all except the first thread, because the first thread has no previous thread, so it doesn't need to add anything. So all except the previous threads will go. They will get the partial sum of the previous thread in position 0. So that's the sum of all the previous threads values, and it's going to add them to all its elements. So it's going to iterate 8 times over each of its elements here for the entire thread log. And then what we will do is we'll have the threads write these values from global memory to shared memory in a coalesced way. So every thread is going to write out 8 values, but it's not going to write out its contiguous chunk of 8 values. We're going to group them together. We're going to write block dim values and then the next block dim values and then the next block dim values in a coalesced way. So that's what this last loop over here is doing. We iterate 8 times, and every time we're going to write out a chunk that is block dim in size where every thread writes out a consecutive value. Okay, I apologize. It seems I copied the wrong directory. So sorry about that. So let me compile this. Okay, and I'll run it. Okay, and as you can see, if you remember before, we had around 0.7 in our implementation. So now the performance has been reduced. I'll run it again. Right, so we'll get a reduction, an improvement in performance, and that's coming from the improvement in the work efficiency of the kernel. Okay. Okay, and this over here is the code that we were supposed to live code. I apologize for what happened. Okay. All right, so having finished about thread coursing, I want to talk about now how we are doing the segmented scan across thread blocks. So far been kind of assuming that we had that, but let's go back and talk about how it's done. When every thread block does a scan of its own segment and contributes its partial sum, we have to go and scan these partial sums and then add them back to these elements. So how do we scan these partial sums? Well, one way to do it is by terminating our kernel, launching a new kernel that will the same scan kernel, but launching it now on the partial sums array to scan the partial sums, right? And then launching another kernel that's going to do the addition, right? And that's what my code right now is doing. However, what this does is what happens here is that this involves launching multiple kernels, right? You have to launch a kernel, wait for it to finish, launch a new kernel, wait for it to finish, launch a new kernel, wait for it to finish. The CPU is kind of busy with launching these different kernels. Also, we lose these values that are in shared memory, right? Because these values here are in shared memory. We have to go store them back to global memory, and then launch this kernel again to scan the partial sums. And then when we launch this add kernel, we have to go load these values again from global memory to shared memory so that we can add to them and then store them back to shared memory. So we lose the opportunity to kind of directly, while these values are still in shared memory, do the addition on them. So these are the disadvantages of launching multiple kernels to do the segmented scan. So the question is, can we do all of this in a single kernel that allows us to keep our data in shared memory so that we can eventually do the addition on it? And it also frees up the GPU to do other things. And also, if we're using this scan operation inside of another kind of bigger computation, like a filter or some other operation that uses scan, right? It's inconvenient to have to kind of terminate the kernel and then launch a new one and then bring everything back to the SM that you need. So how can we do this scan operation without having to launch these multiple kernels? So there's a way to do it, which is we refer to as the single pass of launching a new kernel to scan these partial sums. What we can do is we can have these thread blocks synchronize with each other somehow in order for them to do the scan of the partial sums. What we can do is the following. We can have the first thread block. It produces to scan the partial sum. Once the first thread block produces its partial sum, right? We can have the next thread block wait for it, and when it's done, the next thread block will go grab that partial sum, right? And it will add it to its own partial sum to produce now the partial sum of the two thread blocks combined. The next thread block can wait for that, right? So it'll sit there, and then so here now, once this thread block has added these two partial sums, it doesn't have to wait for all the other thread blocks. It can go ahead and proceed with adding the partial sum of the previous thread block to its own values. The next thread block can do the same. It'll wait for the previous thread block to finish this addition, right? And once it's done, it'll take its own partial sum and add it to produce the partial sum of all the three thread blocks, right? And it can also then go ahead and add the partial sum of the previous two thread blocks to its own values, okay? And then we can do the same thing over here. This thread block can wait for the previous partial sum, and when it's ready, it can add it to have the final partial sum, and also it can go ahead and add this partial sum to its own values. Okay, so this is a single pass scan where we're going to use a single kernel in order for us to wait for the previous kernels. So there's some kind of serialization here, right? Only in this stage where we are doing the scan, the scan across the blocks, there's a sequential scan happening where every thread block waits for the next one and then releases the next one, waits for the previous one, then releases the next one. Okay, but then the additions are all still happening in parallel, and these scans in the beginning are all happening in parallel. So this single pass scan has the advantage of we can keep the data in the SM, and we also don't have to busy the CPU with launching multiple kernels and can go and do other things. Okay. Now to do the single pass scan, we have to we have to have these flags. We have a flag for each one of these thread blocks, and we have the next thread block will have to kind of spin lock on the flag for the previous thread block to make sure that it finishes. We have to make sure that we get our thread fences right so that the data that is written by one thread block to global memory is visible to the next thread block. Because I only have 1 hour and I'm at the end of the hour, I'm not going to go into the code for doing this. The code is available in the book. It's kind of a section at the end of the book, so you're welcome to refer to that as well. Normally, I have an hour 15-minute lecture, so I code this as well. But today we're not going to have time to do that. Okay, so this is how the kind of singlest pass scan works. And in Thrust, Thrust does something similar to this. Thrust and Cup do something a little bit better called decoupled look back, and I'll talk about what that is shortly. But I'll leave it for Jake to cover that in more depth in his lecture. Okay, so other optimizations that we can do for scan that we didn't have time to cover in these 2 lectures. So one of them is using warp level primitives, right? So what we've done is we've taken the scan, we've segmented it across blocks, and then within the block we segmented across threads. But we ignored warps, right? But warps are important because warps the threads in the same warp can synchronize with each other in a faster way than threads across the entire block. So one common optimization for scan is not just to segment directly from the block to the thread. What we actually do is we segment from the block across the different warps, and then we have every warp do its own scan, and then we take the partial sums of the warp scans and we kind of go back and have every warp add the partial sums of the previous warps to its values. This actually gives us significant performance improvements because it allows us to do the scan iterations within the warp without having to do any sync threads. And you know, the scan is a latency bound operation. The sync threads is a significant bottleneck in this operation. So getting rid of these sync threads by doing the scan at the warp level does significantly improve performance. This requires us to use shuffle instructions. Register tiling is also useful. So when we applied thread coarsening in the context of for the threads, we were using shared memory to store the values for the threads, but we can actually bring them to the threads registers, improves performance, the register tiling. And then finally, decoupled look back. So when I covered this, that was the code for the dynamic. That was the code for doing this operation right here. So when we covered this, when I covered this, I told you that we're going to have every thread block wait for the previous thread block, but we actually don't have to do that, right? Instead of having every thread block wait for the previous thread block, which creates this serialization across the blocks and becomes a critical path in our computation, what we can have is we can have the thread block look back. Instead of just one block, it can look back at multiple thread blocks. And if, for example, so here, if block 3 comes and it finds out that block 2, the sum of block 2 and block 1 and block 0 is not ready, but it finds out that block 2's partial sum is ready and block 1's partial sum is ready and block 0's partial sum is ready, instead of block 3 waiting for block 2 to wait for block 1 to wait for block 0, which creates the serialization, what block 3 can do is it can go and get the partial sums of block 2, block 1, and block 0 and add them together itself, and then go on and continue with its add operation. The advantage of that is now we no longer have this serialization chain, right? Block 3 doesn't strictly have to wait for block 2 to finish, which has to wait for block 1. It can go and check if the previous ones have finished. And this idea of a block waiting for a previous block, this is what look back is. And what I've described here is kind of single look back, but decoupled look back is this idea that we look back multiple blocks until we reach kind of until we kind of reach a block that has actually finished its scan, and then we stop there. So we look back gradually, and we kind of gradually look back on, depending on who's that. That's the idea of decoupled. Okay. So these are some additional optimizations, and with these optimizations and a few others, right? That's where we get all the performance that we get from scan, and these optimizations, or some of them, are recurring optimizations. So the idea of dividing from the block to the warp, and then dividing the warp from block to the warp, and then from the warp to the threads, and doing thread coarsening at the level of threads, doing the register tiling at the level of threads. This is something that we see in kind of many of the kernels that we optimize. So in reduction, we do the same thing. Even in matrix multiplication, right? We have this hierarchical tiling where we tile at the block level, and then tile at the warp level, and then tile at the thread level. We do the register tiling at the thread level, and all of that helps us improve performance. Okay. So that is the end of today's material, and I'd be happy to take questions. Try to time it to take the full hour.
Sweet. Thank you so much, Azad. Really, really appreciate it. Everyone, please give a big round of applause for Azad, and thank you for this. Yeah, like I guess we're happy to start taking any questions like from the audience. Like, you can just give folks a few minutes. I guess while we're waiting for people, why are the warp level intrinsics called shuffle? Like I never understood that. Like, why use the word shuffle for this stuff?
I feel like you're shuffling data around, like you're moving things around, and you're doing it very quickly, so it feels like you're shuffling. But yeah, I guess you have to ask the NVIDIA folks why they decided to call it shuffle.
Is that
yeah,
maybe
I think
this?
the name's intuitive, right? Go ahead.
You may know this. Does the shuffle instruction resemble AVX shuffle too?
Right. Yeah.
So I think what we did was, I think we probably took the term from somebody else who had already coined it for the shuffle. Maybe that is a historic reason, and I do not know. Okay, I'm just giving an opinion which may not be correct at all. Yeah, even otherwise, right? Scan, even though looks so simple, so easy, the versatility and diversity of its usage is enormous. It is used in many of the generative AI applications too, even though many people do not even realize it's being used. It is used as primary benchmark for memory bandwidth tests in almost every single machine or a hardware that gets created. So understanding scan, including the decoupled look back kind of methods, are very, very, very important.
Right.
Yeah, but for what it's worth, I think it sort of became even more important with like some of the sort of newer architectures like Mamba and S4. I think we've had like
That's
open
correct.
issues in PyTorch asking for a faster scan implementation. So I guess like, this is like maybe a good call to action for us to go figure this out.
Yeah, so you are right. Mamba, like architecture, the SSM based architecture, without scan, it would not have existed. So whenever you want to go for a long context lens and everything, right? So it's such a small kernel, but the impact is so enormous.
Sweet. I guess if there's no other questions, I think we can stop it here. Like I guess like Azat will probably share slides with us later, and I'll put them on the CUDA mode lectures, and the recording will be available in a few days. If you like this lecture, we have like a few more lectures coming up in the next 2 weeks. Like tomorrow, we have Kate Daniel from Anyscale who's going to be talking about speculative decoding in VLLM. Next week, we have like a very hyped up lecture on Friday, which is going to be about tensor cores. So this is like content that doesn't really exist all that much online. So thank you, Vikram, for setting that up. And then on Saturday, next Saturday, will be another follow-up to this lecture, which is an advanced scan, which is going to be going over some of the more advanced algorithms that like Azat was talking about. And that'll be presented by Jake and Georgie, who already gave the LM.C++ talk. So yeah, thank you so much, everyone. Always a pleasure to see folks, and see everyone tomorrow. Thank you.